Okay, so right here we're filling up our cuvettes with the dilutions. All right, now that we're close, we got to make sure that we get the meniscus exactly on the line. And there you can see the bottom of the meniscus is resting. We repeated this with our other two dilutions and a blank to zero the spectrophotometer. So before we head to this spectrophotometer, we've got our unknown water, ammonium, and dilutions 1, 2, and 3.
So first things first, unmark it and then figure out what way to
Alright, so after wiping the cuvette down and making sure we get the wipe down sides towards the light bulb, we're going to zero it. Alright, we're going to use the stock solution and test it to decide which wavelength to use. So we decided that 606 was going to be our wavelength, and now we're going to zero it again and scan all of our dilutions and the unknown on this wavelength.
Once again, he's going to wipe the sides of the cuvette. He's going to insert dilution 1.
Yes, save my flash drive.
In.
He might also want to.
These are our absorbance values for the 0 and dilutions 1 through 3, and then the unknown. We scanned on a 606 nanometers wavelength.
Okay, so Beer's law is that absorbance is equal to our constant times the path length times concentration plus 0, which is just a y equals mx plus b slope, with our b being 0, our slope is going to be our constant, and concentration is going to be our x value, with b being just 1. Okay, so on our graph we have our x-axis being concentration in molar times 10 to the negative 4th, and our y-axis is going to be absorption in percentage. It's a linear relationship, so as concentration of the solution increases, our absorption also increases.
So we put all of our values into an Excel spreadsheet, and this was the equation of that line with a R value of 0.99.
Okay, so for our stock solution, our molarity was 0.0207, and we used that solution to make our first dilution. We calculated the volume delivered into the volumetric flask, and then we calculated that the number of moles in it by multiplying the volume by the molarity, which gave us this number. Then we divided the number of moles we had by the volume of the volumetric flask, which ended up giving us a molarity of this value.
Okay, so the reason we had to scan across all the wavelengths is because we're looking for peaks, and where the peaks are is where some of the light was reflected. So in this case we had a blue solution. So if we were to scan on an individual wavelength of like red or orange, it would absorb almost all of it, so our absorbance rates would be extremely high, and it would be hard to tell the difference between the different dilutions if we used a different wavelength specifically.
So we use specifically the wavelength of blue light because that will tell us how much our concentration of our dilution will be, because the more concentrated it is, the more blue light will get reflected and not absorbed by the sensor. So the higher the absorption of the sensor would mean the lower the concentration of the solution.